I want to start today by talking about a very specific kind of language barrier.
Okay.
And no, I don't mean trying to order coffee in another country, though, that's stressful enough. I'm talking about a fundamental barrier that exists right inside the machines we all rely on.
You're talking about the gap between the physical world and the digital world.
Exactly. I mean, think about it. The physical world reality, it speaks in heat, in pressure, in stress.
Mm-hmm.
If you stretch a metal bar, that metal resists the pull. That's the language of physics. But then you have the computer, the controller, the brain. It doesn't understand stress. It's just silicon. It only gets one thing.
Voltage,
Voltage.
or sometimes current. But yeah, it's the classic translation problem.
Yeah.
You've got a sensor like a thermistor measuring temperature, and physically it's shouting, my resistance is 120 ohms.
Right.
And the computer's just sitting there going, I have no idea what that means. Give me 0 to 5 volts or give me nothing.
And that translation gap is exactly where our deep dive is today. We're not talking about the sensors themselves or the computer code. We're looking at the translators in the middle, specifically passive bridge circuits and dividers.
Which I'll admit does sound a little bit like we're about to get into civil engineering.
Or maybe burning bridges with your ex.
Let's not go there.
Agreed. But looking at our source for today, Curtis D. Johnson's process control instrumentation technology, it's so clear that these circuits are the unsung heroes of precision measurement.
Oh, absolutely. In analog signal conditioning, this is the foundation.
Yeah.
We're talking about how we convert those physical changes, that change in resistance,
Mm.
into an electrical signal without, any active power amplification at first. It's about using simple parts in really clever ways.
So our mission today is to figure out how a handful of resistors can turn raw reality into readable data. And I think the key thing is going to be that passive does not mean simple.
Not at all. There's a lot of elegance hiding in these circuits.
So let's start with the most basic tool in the toolbox, the voltage divider. This is kind of the hello world of electronics, isn't it?
It really is. If you look at the schematics, it's the simplest setup you can imagine. You've got a voltage supply, a battery, and two resistors in series. We'll call them R1 and R2.
Okay.
And the idea comes right from Ohm's law. You put a voltage across two resistors, and it drops across each one proportional to their resistance.
Okay, so let me just picture that. I have a 10-volt battery, two identical resistors.
Yeah.
The voltage just splits evenly, 5 volts on each.
Exactly. It divides the voltage based on the ratio.
So to make this a sensor interface, I just swap one of those resistors for my sensor, like a thermistor that changes resistance with heat.
Right.
As the temperature changes, the resistance changes, that messes up the ratio, and boom, I measure that change in voltage and I know the temperature.
In theory, yes. You measure the voltage across that sensor, we call it the output voltage, and you have a signal. It seems like the perfect simple solution.
I feel a but coming on. When something in engineering looks this simple, there's always a trap.
There are actually 3 traps. The text points out 3 pretty big gotchas with using a simple voltage divider for any kind of precision work.
Okay, lay 'em on me. What's the first deal breaker?
The first one is nonlinearity.
Meaning the output doesn't move in a straight line.
Exactly. And that's counterintuitive, right? Because Ohm's law is linear. But if you look at the math, the output voltage is the supply voltage times the sensor resistance, divided by the sum of the two resistors.
Okay, I'm picturing the fraction. The sensor resistance is on top.
But it's also on the bottom, in the denominator, and that's the killer. As the sensor resistance goes up, the denominator also goes up. So the voltage doesn't rise in a nice, clean 1-to-1 ratio. It curves off.
So if my temperature goes up 10 degrees, my voltage might jump 1 volt. But the next 10 degrees, it only goes up, what, 0.8 volts?
Precisely. Which means your computer now has to do all this complex linearization math to figure out the real value. It's messy.
Okay, messy, but I guess you could fix that in software. What's problem number 2?
Number 2 is a lot harder to fix. It's a physical thing called loading effects.
Loading. This is the observer effect, right? The act of measuring something changes it.
You've got it. Imagine you hook up a voltmeter to read the voltage. That meter isn't invisible. It has its own internal resistance. By connecting it, you're basically adding another path for the current to flow.
I always think of checking tire pressure. You push the gauge on the valve and you hear that little tsh of air.
That's a perfect analogy.
You have to lose some air to measure the air, so by checking it, you actually lower the pressure.
Exactly. And in our circuit, by connecting that load, the meter, you draw a current away. The voltage drops. The source calls this the Thevenin equivalent. Basically, the number you see on the screen is lower than what was actually there before you touched it.
That's just pure error. Okay, what's the third problem?
Power dissipation. Yeah, heat. To get a voltage reading, you have to push current through the sensor. And current through resistance, it generates heat. I squared R losses.
I can see the problem here. If I'm using a thermistor to measure temperature,
You are heating up the sensor by measuring it. It's called self-heating error. You might make the sensor report that it's 5 degrees hotter than it really is.
Yeah.
Just bad data.
So the voltage divider is simple, but it lies to you three different ways. It gives you a curved output, it collapses when you look at it, and it cooks itself.
A bit harsh,
Yeah.
but yeah, pretty accurate. We need a better way.
Enter the wheatstone bridge.
Classic.
Visually, it always looks like a diamond shape to me. But what's really going on? How does it solve those problems?
The easiest way to think of it is as two voltage dividers sitting right next to each other in parallel.
Okay, two dividers. But isn't that just doubling the problems?
The magic is in where you measure. With a single divider, you measure across one resistor relative to ground. In a wheatstone bridge, you measure the difference between the two dividers, across the middle of the diamond.
So you're comparing the two sides against each other. It's a differential measurement.
Exactly. And this gets us to the most important concept in all of this, the null condition.
The null. Sounds a bit existential.
It's actually just beautiful engineering. The bridge is balanced or nulled when the voltage difference between those two middle points is exactly zero.
So the potential is exactly the same on both sides. No current flows between them.
Correct. And for that to happen, there's a golden rule. The ratios of the resistors have to match. Or, as the text puts it, the cross products must be equal. R1 times R4 has to equal R3 times R2.
Okay, I get the math. But why is zero such a big deal? Why is aiming for zero better than just measuring, say, 2.5 volts?
Because zero is a rock-solid reference. Think about amplification. If you're measuring around zero, you can amplify that signal massively. A tiny shift of, say, 0.0001, you can boost that 1,000 times to 1 volt and read it clearly.
Whereas with the old voltage divider, my signal is sitting on top of this big DC offset. It's sitting at 2.5 volts.
Right. Try to amplify that by 1,000, and you'd need a system that can handle 2,500 volts. You'd rail the amplifier instantly.
It's like trying to hear a whisper. If you're in a silent room, that's the null whisper is obvious. If you're at a rock concert, the voltage divider, good luck.
Fantastic analogy. And there's another huge benefit. The null is independent of the power supply. If your battery drains a little, drops from 10 volts to 9, well, zero is still zero. The balance holds.
This makes it incredibly robust.
Okay.
Okay, so the bridge is better, but you still have to get the signal out. And the text says, this is where it gets messy again, right, with detectors.
Right. How do we see that zero? Historically, you'd use a galvanometer.
The little analog needle gauge.
Exactly. The problem is, just like our voltmeter before, a galvanometer is a physical device. It's a coil of wire. It has resistance. It becomes part of the circuit.
So we're back to the loading problem.
To an extent, yeah. To calculate the error it causes, you have to find the Thevenin equivalent of the whole bridge. It's a mathematical nightmare.
Which is why we don't really use them much anymore.
We don't. Today you'll find op-amps, operational amplifiers.
And how do they help?
Impedance. An ideal op-amp has infinite input impedance. It looks like an open circuit. It draws almost zero current.
So the bridge doesn't even know it's being watched.
Pretty much, yeah. It makes the math so much cleaner. We can just focus on the resistors and not worry about the detector dragging the voltage down.
Okay, speaking of dragging things down,
Yeah.
let's talk about wires. The text brings up the long wire problem.
Yes. The bane of instrumentation.
Because your sensor is never sitting right on the circuit board, is it? It's out on a pipe maybe 100 meters away.
Exactly. And copper wire has resistance. It might only be a few ohms, but it's there. You run wire out to a sensor and back, you've just added 5 or 6 ohms to that leg of the bridge.
And the bridge doesn't know the difference. It just sees total resistance.
It gets worse. Resistance changes with temperature. So if the sun comes out and heats up that long run of wire,
The resistance goes up.
and the bridge reports a change. But it wasn't the sensor, it was just the weather.
That's unacceptable. So how do you fix it? The text has a diagram for something called lead compensation.
It is a brilliant, brilliant fix. The Siemens 3-wire system. Instead of 2 wires to the sensor, you run 3.
Wait, wouldn't more wire just add more resistance?
It's all about geometry. You arrange it so 1 wire carries power, but the other 2 wires are placed in opposite legs of the wheatstone bridge.
So one wire is in the sensor's leg and the other wire is on the opposing side of the bridge.
Exactly. Think of it like a balance scale. If you add weight to both sides at the same time,
Nothing happens. The balance stays level.
that's lead compensation. If the sun heats up the wires, wire A's resistance goes up, trying to pull the bridge one way. But wire B's resistance also goes up, pulling the bridge the other way by the exact same amount.
They cancel each other out.
Perfectly. It's a real aha moment in engineering. You don't eliminate the error, you just make sure it affects both sides equally so it disappears.
That is just so clever. Okay, so moving on. Manually turning a knob to find zero sounds tedious, especially in a factory.
It is, so we need automation. The text introduces the current balance bridge.
How does that work?
Instead of changing a resistor to get back to zero, you leave the resistors alone. You inject a specific amount of current into one of the nodes to force it back to zero.
You sort of push it back into balance.
Exactly. And since we can control current electronically with incredible precision, a computer can null the bridge instantly.
So the measurement isn't the voltage anymore, it's how much current did I need to shut this thing up?
That's it. And that current becomes your signal. It's linear, it's fast, it's easy to digitize.
Okay, that brings us to another layer of complexity. AC bridges. We've only been talking about resistance.
Right. We're moving from resistance R to impedance Z.
Yeah.
If you want to measure something like capacitance, say a level sensor in a tank, a DC battery just won't work.
Because a capacitor blocks DC current.
Mm-hmm. You need an AC signal, a sine wave, and this is where the math gets imaginary.
I always love that term, imaginary numbers.
It sounds fake, but the consequences are very real. When you balance an AC bridge, you have to balance two things at once. The real part, which is the resistance, and the imaginary part, which is the reactance or the phase shift.
The timing of the wave.
Yes. A capacitor delays the voltage. If you don't balance that timing delay, you'll never get a true null. You might get the voltage down, but the phase is wrong, so it never hits zero.
So it's trickier. Okay, let's ground this again. The text has a great section on mechanical sensors that ties this all together with strain gauges.
Yes, the strain gauge is the poster child for the wheatstone bridge.
So what is it? What's a strain gauge?
It's basically a thin foil pattern, like a tiny maze of wires glued to a surface. You stick it on a beam, say on a road bridge. When the beam bends, the foil stretches.
Is this a tiny bit?
Microscopic. As it stretches, the wire gets longer and thinner, and its resistance goes up. But the change is maybe a few milliamps. A multimeter would never see it.
So you need the bridge.
You absolutely need the bridge to even detect it. But then you have that temperature problem again. If the sun hits the steel beam, it expands, and the gauge resistance changes. How do you know if it's a truck or just a hot day?
How do you fix that?
The source describes a trick called the dummy gauge.
Sounds a bit rude.
It's the technical term, but it's brilliant. You mount one gauge,
Yeah.
the active one, so it stretches with the beam. Then you mount a second, identical gauge, the dummy, right next to it, but you turn it sideways so it doesn't stretch.
So it's on the same metal, the same temperature, but it can't physically feel the strain.
Exactly. You wire them into adjacent arms of the bridge. If the temperature goes up, both gauges increase in resistance by the exact same amount. And because of that bridge ratio rule,
They cancel out, the output stays at zero.
right. But when a truck drives over,
Only the active gauge changes. The bridge goes off balance and you measure the strain. You've completely erased the environment from the data.
that's the trick. And you can take it further. If you use 4 active gauges, 2 in tension on top of the beam, 2 in compression on the bottom, you can quadruple the sensitivity of the measurement.
It's amazing, all that strategy just to measure a tiny bend in a piece of metal. It's not just plugging in a wire, it's geometry and thermal compensation.
That's the real lesson. Precision isn't about buying a more expensive sensor. It's about building a system that cancels out the errors.
So to wrap up, we started with the voltage divider. Simple but flawed. Nonlinear, gets loaded down, heats itself up.
Good for rough estimates, not much else.
So we upgraded to the wheatstone bridge, the diamond. It uses a null condition to get extreme precision and immunity to power supply drifts.
The gold standard.
We solved the long wire problem with the 3-wire system, canceling resistance. And then we saw how strain gauges use dummy partners to cancel out temperature.
That's a perfect summary.
But before we go, I want to leave the listener with one final thought. We keep talking about how great the bridge is because of the null, but we don't always use it at null, do we?
That is the final provocative thought. The source explicitly warns about the loss of linearity. The bridge is perfect when it's balanced at zero. But the moment you go off null, which you have to do to get a reading, the voltage output is actually, well, nonlinear.
So the bridge itself is telling us a lie.
It's telling us a curved truth. We usually just rely on software to linearize the data,
Hmm.
or we assume the change is so small it doesn't really matter. But physically, deep down, the relationship is curved.
It's a reminder that even our best tools have their own sort of distorted view of reality. We build these perfect zero structures, but as soon as the world interacts with them, things get bent.
A curved truth. I like that.
So the next time you step on a digital scale or adjust your thermostat, just remember, there is probably a tiny diamond of resistors inside, fighting against temperature, wire resistance, and the laws of linearity, just to tell you a number.
Thanks for listening to this deep dive into passive bridge circuits.
Always a pleasure.
We'll see you on the next one.